Welcome to Professor Explains. Tonight, before you let the day fall away from your shoulders, I want you to picture something almost impossible. Picture a volcano, not a volcano in some warm green valley with the smell of sulfur on the wind and ferns growing right up to the edge of the heat. No. Picture a volcano pushing its slow red breath up through ice. A kilometer of ice. Ice so thick that the whole weight of a mountain of frozen water sits over the rock. And still, from somewhere far below, in the deep furnace of the planet, the heat rises and finds a crack and exhales. And here is the strange part. That volcano is not at the pole. It is not in some far northern place where you would expect a frozen world. It is sitting almost exactly on the equator, the middle of the planet, the band of the globe that today holds the rainforests and the warm, shallow seas and the long, lazy beaches where the sun never really leaves. There, where you would expect heat, there is ice a kilometer deep and a volcano breathing through it very quietly into a sky that has not seen open water in a very long time. This is not a fantasy. This is, by the best reading we have of the rocks, something that genuinely happened to our world. More than once. And the puzzle at the heart of it, the thing that kept geologists turning it over for years, is not really how the planet froze. We can imagine freezing. Freezing is easy to picture, the puzzle is the opposite. If the entire planet had been sealed in ice, if even the equator was locked under a kilometer of frozen ocean, if the whole world had become a single white mirror flinging the sunlight back into space, then how, by any mechanism at all, did it ever get warm again? How does a frozen planet thaw itself? What broke the freeze? For a long time, nobody could say, and that is the question we are going to walk down into tonight, slowly. The way you walk down into a cellar with a single lamp, letting your eyes adjust one step at a time. There is no rush. The answer is millions of years old, and it has waited this long. It can wait for us to get there gently. So settle in, let your head find the pillow properly, let your jaw unclench the way it does without being told to when you finally stop holding the day. We are going somewhere very old and very cold, and then, much later, somewhere astonishingly warm, and the journey is a long one. Before we go any deeper, I always like to know where in the world you are listening from tonight. It does something to a story this old and this lonely, knowing there are people scattered all over a planet that once was frozen end to end, all settling down to sleep at the same time. So if you feel like it, leave a note somewhere of where you are, a city, a country, a time of night. I read them, and if you are new here and you would like more of these slow journeys into the strange corners of how the world came to be, you can quietly subscribe, and we will go somewhere else, old and good together, another night. There. That is the only time I will ask. Now, we go down. Let me give the frozen world its proper name because scientists have one for it, and the name itself is part of the wonder. They call it Snowball Earth, the Snowball Earth hypothesis. And it holds something that sounds, and the first time you hear it, like an exaggeration, like the kind of thing a child says about how cold it was on the way to school. It holds that for a long stretch of the deep past, ice did not just cover the poles the way it does today, in two white caps at the top and bottom of the globe. The ice advanced. It crept down from the poles year by year, century by century, the way frost creeps across a window in the night. And it did not stop where ice usually stops. It kept going, down past the cold latitudes, down past the temperate band where most of us live, down into the tropics until the ice sheets from the north and the ice sheets from the south reached out across the warm middle of the world and met. And the planet, the whole planet, was wrapped in ice. This happened during a chapter of Earth's history called the Cryogenian period. And even the name is a kind of poem because cryogenian comes from the same root as cryogenic, the word we use for things frozen impossibly cold for the deep freeze of the laboratory. The Cryogenian, the age of the great freezing. It runs in the count of the rocks from roughly 720 million years ago to about 635 million years ago. Say those numbers slowly to yourself. 720 million years. Long before there were animals walking on land. Long before there were forests or flowers or anything you would recognize as a creature with eyes. The most complicated living things on the whole planet then were small, soft, simple things in the sea. And over their heads, the world turned to ice. Now, when you first hear a claim like that, ice all the way to the equator, the honest part of your mind should push back a little. It should say, how could anyone possibly know? Nobody was there, there were no thermometers, no satellites, no one keeping a diary of the weather 670 million years ago. So how can a geologist stand up tonight in front of a class and say with a straight face that ice once reached the tropics? It is a fair question, and the answer is one of the most beautiful pieces of detective work in all of science, and it is worth slowing right down for, because it is the foundation under everything else we are going to say. The clue is written into the rocks themselves, and it comes in two parts. The first part is the rocks that ice leaves behind. When a glacier moves, it is not clean. It is not a tidy sheet of skating ice. It is a slow, grinding bulldozer. It scoops up rubble, sand, gravel, boulders, all sizes mixed together, carries it along frozen inside the ice, and when the ice finally melts, it dumps that jumbled mess in a heap. Geologists have a name for that frozen and dumped rubble once it has hardened into stone. They call it tillite, a rock made of glacial garbage, all the sizes thrown together with no sorting, the unmistakable signature of ice that has been on the move. And there are other telltales. There are drop stones, single large stones that fell out of the bottom of floating ice and plunged down through still water and landed in fine mud, punching down into layers that were soft when they landed. You can see frozen in the stone the moment a boulder fell from an iceberg and struck the sea floor. That is ice. There is no other good way to drop a heavy stone into the middle of fine, quiet mud. So the rubble tells you there was ice. But the rubble alone does not tell you where the ice was. The poles have always had ice, more or less. Finding glacial rubble is not by itself a shock. The shock is the second part of the clue, and this is the part that turns a curiosity into a revelation, because the rocks remember not only that ice was there, but where on the globe they themselves were lying when the ice came. The rocks carry a memory of latitude. They carry, locked inside them, a record of how close to the equator they sat all those hundreds of millions of years ago. And reading that memory is called paleomagnetism, and it is one of the quiet miracles of geology. Here is how it works, and I will go slowly because it is the kind of thing that sounds like sorcery until you see the simple sense of it. Our planet has a magnetic field. You know this already. It is the thing that swings a compass needle to point north. That field comes out of the Earth at the poles and wraps around the whole globe, and the angle at which it dips into the ground changes depending on where you stand. Near the equator, the magnetic field runs almost flat, nearly horizontal, parallel to the ground. Near the poles, it plunges down steeply, nearly straight into the Earth. So the dip of the magnetic field is a kind of hidden marker of latitude. At the equator, flat; at the poles, steep; and everywhere in between, some angle in between, like the hand of a clock that tells you not the time but your distance from the middle of the world. And now the beautiful part. When certain rocks form, when molten rock cools, or when fine grains of iron-bearing sediment settle gently to the bottom of a sea, tiny magnetic minerals inside them act like miniature compass needles. As the rock hardens, those tiny needles freeze in place, pointing the way the magnetic field pointed at that exact moment, dipping at the exact angle the field dipped at that exact spot on the globe. And there they stay, locked for hundreds of millions of years. The rock becomes a tape recorder of the ancient magnetic field. A geologist can take that rock, measure the frozen angle of those tiny magnetic grains, and read off, after all this time, how far from the equator that rock was lying when it formed. And when they do this for the glacial rocks of the Cryogenian, the tillites, the dropstones, the unmistakable rubble of ice, the answer comes back again and again: low. Low latitude, near the equator. The most famous example sits in South Australia, in a place called the Flinders Ranges, in rocks that geologists named the Elatina Formation. The Elatina Formation holds glacial sediments, the rubble of moving ice, and when its frozen magnetic needles are red, they say that this rock was lying within about 10 degrees of the paleo-equator when the ice ground over it. Within 10 degrees of the equator, that is the tropics, that is the warm band of the world. And there, ice was carving the land. Sit with that for a moment. In the dark, glaciers in the tropics, the rocks do not say it loudly, they do not announce it. They just sit there in the Australian outback, in the dry red ranges, holding their tiny frozen compasses, and when someone finally thought to ask them the right question, they answered quietly, "The ice was here, and we were near the equator when it came." That is the proof. Not a guess, not a legend, not someone's wild idea. A measurement in stone that the ice reached the warm heart of the world. So now let us try to feel what that world was actually like, the world the rocks are describing, because numbers like ice at the equator can stay abstract, like a fact on a page, and I want you to be able to stand in it. Imagine the whole ocean, every ocean, the entire connected surface of the global sea, frozen over. Not frozen the way a pond freezes with a thin skin of ice you could crack with a boot. Frozen deep. By the strictest version of the idea, the version scientists call the hard snowball, the ice over the equatorial ocean stood as much as a kilometer thick, a kilometer of solid ice between the air and the water. You could have driven down through it for as long as it takes to drive across a city and still been inside the ice, with the buried sea far below your wheels, black and silent and sealed away from the sky. And the cold, the average temperature of the whole planet's surface in this frozen state may have fallen to somewhere around -50 degrees Celsius. Let that number land, -50. That is colder than almost anywhere a human being lives today. That is the kind of cold that belongs to the dead of an Antarctic winter in the center of the continent, where the air itself feels like it could cut you. And that was not one bad place on the planet. That was the average. That was, more or less, everywhere. The whole white ball of the world turning in space, reflecting the sunlight back the way a mirror does, holding almost nothing of the warmth, locked at a cold so deep it is hard for a warm-blooded creature even to imagine. This is the lockdown. This is the frozen prison the title of tonight's story promises. A planet sealed in ice from pole to pole, a kilometer deep at the equator, averaging 50 degrees below freezing, the ocean cut off from the air, the whole familiar machinery of weather and rain and rivers stopped. And it did not last a winter. It did not last a century. It lasted, as we will see, for millions upon millions of years, the deepest, longest silence the planet has ever known. And the question only sharpens the longer you stare at it. A frozen world like that is, in one sense, very good at staying frozen. We will see exactly why in a moment. White reflects sunlight. Reflected sunlight means lost warmth. Lost warmth means more ice. More ice means more white. It is a trap that, once sprung, seems designed never to release. So how on earth did it ever let go? That is the loop we are holding open, the one we will not close tonight, and not for a long while yet. Hold it loosely, let it hum in the back of your mind like a question you have decided not to answer just before sleep. We will get there. The thaw is coming, but to understand the escape, we first have to understand the trap itself. How a planet falls into a freeze so complete, and why that freeze is so very hard to break. So let us turn now from the picture of the frozen world to the mechanism of the freezing, because the trap has a name, and once you understand it, the whole rest of the story locks into place. The name is the ice albedo feedback. Let me unpack that gently, one word at a time, because it is the single most important idea in the whole night, and everything turns on it. Albedo is just a scientist's word for how reflective a surface is, how much of the sunlight that falls on it gets bounced straight back instead of soaked up. Think of it like the color of a shirt on a hot day. A black shirt has low albedo. It drinks the sunlight, it holds the heat, and you feel it warm against your back. A white shirt has high albedo. It throws the light back, it stays cool, it refuses the heat. Now think about ice and snow. Fresh snow is about as white and bright a surface as the natural world makes. Its albedo is very high. It is a planetary white shirt. When sunlight hits snow and ice, most of it bounces straight back up into space and is simply lost. It never gets a chance to warm the ground at all. Dark ocean, by contrast, is a black shirt. Deep water is one of the darkest surfaces on the planet. It drinks the sunlight greedily and turns it into warmth. So already you can feel where this is going. A planet covered in dark ocean and dark land soaks up sunlight and stays warm. A planet covered in white ice reflects sunlight and stays cold. The surface decides how much heat the world is allowed to keep. And now the word feedback, which is where it becomes a trap. A feedback, in this sense, is a loop that feeds on itself, where the result of a thing makes more of that same thing happen, round and round, each turn pushing the next turn harder. And the ice albedo feedback is the coldest, cruelest loop of them all. Walk it round with me, one slow circle at a time. Suppose the world cools a little, for whatever reason. A little cooling means a little more ice forms spreading out from the poles. More ice means more white surface. More white surface means more sunlight reflected back into space. More sunlight lost means less warmth kept. Less warmth means the world cools a little more. And a little more cooling means, yes, a little more ice. And round it goes again. Each loop makes the next loop easier. Each step down the stair makes the next step steeper. The ice does not just grow, it accelerates its own growing. For most of Earth's history, this loop is held in check. There are other forces pushing back, keeping the ice penned up near the poles, and the balance holds. But the climate scientists who modeled this, building on the work of a researcher named Boudico back in 1969, who built one of the very first mathematical models of this exact balance between sunlight and ice, they found something chilling hidden in the equations. They found a tipping point, a line of no return. And the line sits at roughly 30 degrees of latitude. That is about the latitude of the deserts of southern Egypt, of the top of Australia. If the ice ever manages to advance that far, if the white edge of the ice sheets creeps down past 30 degrees from the poles, then the loop becomes unstoppable. Past that line, so much of the planet's surface is white, so much sunlight is being flung back into space, that the cooling can no longer be reversed by anything gentle. The feedback takes over completely and the ice does not creep anymore, it races. The models suggest that once the ice crosses that 30-degree threshold, it can run all the way to the equator and seal the planet shut in as little as 1,000 years. 1,000 years. After billions of years of an open, living blue and brown world, the whole thing can flip to white in a span of time shorter than recorded human history. There is no slow, gentle slide into the deep freeze. There is a long stability, and then an edge, and then a fall. The planet does not wade into the ice. It tips over a cliff and lands frozen. So that is the trap. That is why a snowball world is so hard to escape and, it turns out, so easy to fall into once you get too close to the edge. But a question remains, and it is a good one, to drift toward sleep on. What pushed the world that close to the edge in the first place? The loop only runs away once the ice has already reached 30 degrees. Something had to do the early, patient work of cooling the planet down to that brink before the feedback could take over and finish the job. Something had to walk the world up to the cliff. So what was it? The rocks suggest a few hands on the planet's back, all pushing in the same cold direction. And the first one is almost unbelievable because it has nothing to do with the Earth at all. It has to do with the sun. We think of the sun as a constant, the one fixed, faithful thing, the same yellow lamp that has hung in the sky every day of every life that has ever been lived. But the sun is a star, and stars change slowly over enormous spans of time. And our sun has been very gradually, very patiently brightening for its whole long life. It burns a little hotter, a little brighter, every few 100 million years. Which means that the further back you go, the dimmer the sun was. And in the Cryogenian, the time of the Great Freezing, the sun was not as strong as the one warming your window this morning. It was, by the best calculations laid out by a scientist named Guff in 1981, about 6% fainter than it is today. 6% does not sound like much. You would not notice if someone turned the lights in a room down by 6%, but spread that dimming across a whole planet, across every square meter of ocean and land and ice, and held for millions of years, and it changes everything. It lowers the baseline. It means the world was already running a little colder than ours, a little closer to the freezing edge all the time, with the heating turned down low. We call this the faint young sun. A younger, dimmer star holding the planet at a cooler resting temperature so that it took less of a push to send the whole thing over the cliff and into the runaway. The thermostat of the whole world was set lower than it is now, and a lower setting means a shorter fall to the ice. So the faint young sun set the stage, but a dim sun alone does not freeze a planet. The world had managed the dim sun for a very long time without turning to ice. Something else had to give the final shove, something happening on the Earth itself, right at the start of the Great Freeze. And here the story turns to one of the grandest, slowest dramas the planet stages, the wandering and breaking apart of its continents. The land we walk on is not fixed. Over hundreds of millions of years, the continents drift across the face of the globe, slow as the hour hand on a clock you cannot see move, carried on the great churning of the rock beneath. They gather together into single, vast supercontinents, and then after a long while, they crack and split and drift apart again. And in the time leading up to the Cryogenian freeze, there had been one great supercontinent, a gathered mass of nearly all the world's land, sitting, as it happened, mostly in the warm tropics near the equator. Its name was Rodinia. And in this story, the crucial thing about Rodinia is that it was breaking up. splitting apart along enormous cracks the way old ice cracks on a lake, opening new seaways between the pieces. Now, why should the breaking of a continent cool the whole planet? The answer is one of the quiet, patient ways the Earth controls its own temperature, and it works through rain and rock. When a great landmass cracks open near the equator, it exposes huge surfaces of fresh, raw rock to the warm, wet, tropical air. And the equator is where the rain falls hardest. Rain falling on bare rock year after year does something slow and chemical. It weathers the rock, it eats away at it. And in eating at certain kinds of rock, it pulls carbon dioxide, the warming gas, the blanket gas, out of the air and locks it away into the ground and the sea. The more fresh rock you expose to tropical rain, the more carbon dioxide gets drawn down out of the sky, and the thinner the planet's warming blanket becomes, and a thinner blanket means a colder world. And Rodinia did not break quietly. Right at the dawn of the freeze, around 717 million years ago, there was a colossal outpouring of volcanic rock across the tropical part of the breaking continent, across a region geologists call Laurentia, an ancient ancestor of North America. This enormous eruption laid down vast sheets of dark volcanic rock called basalt over an area so large it has its own grand name, the Franklin Large Igneous Province. Sheet upon sheet of fresh basalt spread across the warm equatorial land, and basalt, it turns out, is one of the very easiest rocks of all to weather, one of the hungriest at pulling carbon dioxide out of the air when the rain gets at it. So picture the timing. Right as the Great Freeze was about to begin, the planet had just laid out across the rainy tropics an enormous fresh field of exactly the kind of rock that drinks down the warming gas fastest. The rain went to work on it. The carbon dioxide came out of the sky. The blanket thinned, and the world cooled, and cooled, and cooled, walking step by step toward the 30-degree edge. This is the story written by scientists like MacDonald and his colleagues, who read the dates and the chemistry out of the rocks and matched the great basalt eruption to the moment the freezing began. And now you can feel all the hands on the world's back at once, all pushing the same cold way. A faint, young sun holding the planet cooler than ours, the heating turned low, a breaking supercontinent opening fresh rock to the rain, and a vast new field of hungry basalt at the equator, drinking the warming gas out of the sky as fast as the rain could deliver it. Slowly, patiently, over a long age, these forces walked the world toward the cliff. The blanket grew thinner. The ice crept down from the poles, 30 degrees, the edge, and then the trap sprang. And when the trap sprang, it did not spring gently. The ice albedo feedback, once triggered past that 30-degree threshold, did not pause to allow adjustment. It ran. The reflective surface grew, the sunlight bounced away, the air cooled further, more ice formed, and more sunlight bounced away again. A loop, tightening on itself, each cycle feeding the next with mechanical indifference. The world that had spent perhaps millions of years walking slowly toward the cliff now fell, and fell fast. Climate models suggest the ice raced from those critical mid-latitudes all the way to the equator in as little as 1,000 years. 1,000 years sounds like a long time to a human being. It is 40 generations, the span from the age of the Vikings to this very night. But to a planet that had been building toward this moment for the better part of an aeon, 1,000 years is barely a breath. The freeze was nearly instantaneous. The trap, once sprung, took almost nothing to close. What remained was a world that had never existed before in quite this form, or at least, if it had, the memory of it was buried so deep in time that even the rocks struggled to speak of it clearly. A planet, your planet, the only one, encased from pole to equator in ice and snow. The great tropical seas, which had never stopped moving, never stopped catching sunlight, never stopped being warm in all the hundreds of millions of years since liquid water first arrived on this world, fell quiet. The surface grew still. The kilometers of rolling ocean sank beneath ice sheets that, in the hardest versions of this story, may have grown to be a kilometer thick, even at the equator. The average temperature of the whole globe dropped to something in the region of -50 degrees Celsius. Not a cold winter night, not even a particularly harsh ice age of the kind our own ancestors endured. Something different in kind, not just degree. A world that had been fundamentally structurally altered. A world in a state it was not built to sustain forever. But it would sustain it for a very long time. This is the thing that is easy to hear and hard to truly feel. The freeze did not last a year, or a century, or even a millennium. The cryogenian period, whose name comes from the Greek for cold and for birth. Cold birth, a name chosen with more poetry than whoever named it perhaps intended, stretched from roughly 720 million years ago to 635 million years ago. And within that stretch, the evidence in the rocks speaks not of one great freeze, but of two separate global glaciations, each with its own character, its own duration, its own particular cruelty. 2 times that the planet repeated this sequence, 2 times that it found itself locked inside ice from pole to pole. The first of these is the one called the Sturtian. The name comes from a gorge in the south of Australia, Sturt Gorge, cut into the hills not far from the city of Adelaide in the Flinders Ranges, that ancient spine of rock running through South Australia, where so much of this story was first read in stone. The Sturtian glaciation began at around 717 million years ago. That much, the zircon crystals and rhenium-osmium dating tell us with reasonable confidence. The same patient techniques that read age from the chemistry of mineral grains, the same methods that placed the Franklin basalts at precisely the moment the freezing began. And the Sturtian did not simply begin, freeze the world, and end. It endured. It went on and on and on through what geologists calculate to be approximately 57 million years of continuous glaciation. 57 million years of global ice. To help your mind reach toward that number, 57 million years ago, the ancestors of horses had only recently appeared. The dinosaurs had been gone for nearly 10 million years already. The world we think of as the ancient past, the world of great reptiles and strange seas, was itself new in the context of the Sturtian. The Sturtian glaciation is the longest glaciation in the entire known history of this planet. Nothing else comes close. It ended around 660 million years ago. Why? That question is precisely what the rest of this story is built to answer, and we will come to the mechanism in its proper depth. But it ended. The ice retreated. The world thawed, at least partially, and something like warmth returned to the surface of the equatorial ocean. And then, after an interlude whose details the rocks preserve only imperfectly, the second great freeze began. This one is called the Marinoan. Its name comes from a different place in the same corner of the same country, Merino Rocks near Adelaide, South Australia, a stretch of coastline on the Gulf St. Vincent, where the geological record of this later glaciation is written into the cliff face and the shoreline. The Marinoan began at around 650 million years ago. Compared to the Sturtian, it was almost brief, a few million years perhaps rather than 57. But brief is a relative term. A few million years of global ice is still an interval that contains the whole of human civilization many thousands of times over. And the Marinoan, when it ended at around 635 million years ago, ended with a particular violence that left marks on the rock so extreme, so chemically unusual, that they puzzled geologists for decades before anyone arrived at an explanation capable of making sense of them. Those marks are the cap carbonates, and we will reach them. But first, the names and the timing deserve a moment of stillness because they are not small things. Two glaciations, the Sturtian, beginning 717 million years ago, lasting 57 million years, the longest in Earth's history. The Marinoan, beginning around 650 million years ago, lasting a few million years, ending 635 million years ago with a deglaciation so violent it wrote itself in stone in a form no other period of Earth history has ever replicated. Two events separated by an interval of relative warmth. 2 times the trap sprung, 2 times the ice raced to the equator, and the world fell silent beneath its white cover. The idea that this had happened at all, that the entire planet had once been encased in ice, was not obvious or quickly accepted. Geology is patient, and so is the understanding that grows out of it. The first person to notice something seriously strange about the glacial deposits of this era was a British geologist named Brian Harland, working in the 1960s. Harland was examining glacial sediments, the rubble and till left behind by moving ice sheets, and he found them in places that made no sense if the glaciers that deposited them had been ordinary polar or high-latitude glaciers. He found them at low paleolatitudes. He found them in rock that, by the magnetic fingerprint locked into its minerals at the time of its formation, had been near the equator when the ice lay down. Glacial debris at the equator, ice in the tropics. Harland published his observations, and they were noted, and they were uncomfortable, and they did not immediately produce a full explanation. The idea was too large, the implications were too strange. The full model, the complete mechanistic hypothesis that explained not just the existence of the low-latitude glacial deposits, but how such a state could form, how it might be maintained, and, crucially, how the planet might ever escape from it, came later. It came from a geobiologist named Joseph Kirschvink, who in 1992 contributed a chapter to a book of geological essays in which he laid out, for the first time, the full logic of the global glaciation and gave it the name it has carried ever since, Snowball Earth. A name that is almost childlike in its simplicity and that has proved almost impossible to dislodge from the scientific imagination precisely because of that simplicity. It names the thing. It tells you immediately what you are dealing with. The whole planet, white, a snowball drifting in the dark. Kirschvink's model built on Harland's observations and on decades of work in climate physics. But the name and the coherent mechanistic story are his, and that story, with modifications and refinements and vigorous ongoing debate, is the one we are following tonight. It is the one written into the rocks of the Flinders Ranges and the Elatina Formation and 100 other outcrops on every continent, all telling the same cold tale. Now, the planet is frozen. Both freezes, both the Sturtian and the Marinoan, have begun and played out and locked the world in ice for their respective intervals. And the question that is worth sitting with, quietly, in the dark, the question that should feel genuinely strange if you let it, is this one: how does something like that end? Not how does an ordinary ice age end. Ordinary ice ages end in ways that are now reasonably well understood. Shifts in Earth's orbital parameters, changes in the amount of sunlight reaching different latitudes at different seasons, feedbacks in the carbon cycle and ocean circulation that are broadly within the range of normal planetary behavior. Those ice ages, the ones our own ancestors experienced, were cold, but they were not this. In those ice ages, the tropics remained open ocean. The equatorial belt, even during the most intense glacial maximum of the last 2 million years, was never frozen. The ice sheets advanced from the poles and retreated again, and the whole system remained within what you might call the normal operating range of a planet that has liquid water at its equator. Snowball Earth is different in kind. On a fully frozen planet, the ice albedo feedback is not just running, it is locked. The ice reflects the sunlight. The sunlight cannot reach the dark ocean that would absorb it, and so the ocean cannot warm, and so the ice does not melt, and so the sunlight keeps bouncing away. The trap is self-maintaining. Pull on any of the usual threads that unravel an ordinary ice age, and you find that they do not apply here. There is no dark open ocean at the equator to absorb heat and nudge the system back. The system has run past its normal range of self-correction. It has, in the language of physics, reached a different stable state, a state that, by its own internal logic, has no obvious exit. And yet it exited. Something broke the trap. Twice. The answer lives in a kind of planetary clock that had been running for billions of years before the freeze began, and that kept running through all of it, regardless of what was happening on the surface. It lives in the interior of the planet itself, because whatever was happening at the surface, whatever the ice was doing, whatever the sunlight was or was not doing, the Earth's interior did not freeze, could not freeze. The heat inside the planet, generated by the slow decay of radioactive elements deep in the rock and inherited from the violence of the planet's formation 4.5 billion years earlier, kept working. And where that heat found a way to reach the surface, it did what it has always done. It erupted. Volcanoes never stopped. Through the Sturtian, through the Marinoan, through tens of millions of years of global ice. The volcanoes kept erupting, not loudly, not in a single great event, but steadily, persistently, a background geological breathing that has never ceased in the history of this planet, and that the ice at the surface could not stop, because the ice at the surface is the thinnest of skins over a world that is very largely still molten. Magma rose through the crust in the places it has always found to rise. It pushed up through the ice in some cases, building volcanic islands that stood above the white plain. It erupted at mid-ocean ridges on the ocean floor, far below any ice in the perpetual darkness of the deep sea. And from every eruption, from every vent and fissure and volcanic throat, the same gas emerged that has always emerged from volcanoes throughout this planet's history. Carbon dioxide. Molecule by molecule, eruption by eruption, year by year and millennium by millennium across tens of millions of years, carbon dioxide poured into the atmosphere. Now, on a normal functioning planet, carbon dioxide has a thermostat. It has a mechanism that keeps it from accumulating indefinitely, a negative feedback loop that has been operating for hundreds of millions of years, and that is, in large part, responsible for Earth being habitable rather than either a frozen rock or a scorched one. That mechanism is quiet, invisible, and easy to overlook because it operates so slowly that nothing in a human lifetime would show it. But it is one of the most important processes on this planet, and understanding it is the key to understanding how the snowball Earth escape actually worked. It begins with rain. When rain falls through the atmosphere, it does not fall as pure water. Carbon dioxide in the air dissolves into the falling droplets. It dissolves readily and quickly, the way sugar dissolves in warm tea, and what it forms when it does is a weak acid. Carbonic acid, H2CO3, the same mild acidity that gives fizzy water its gentle bite. This acidic rain falls onto rock, and where acidic water meets certain kinds of rock, particularly the silicate rocks that make up most of the continental crust, the granite and basalt and their relatives, it reacts with them. It dissolves minerals out of the surface. It carries those dissolved minerals away in rivers down to the sea, and in that process of dissolving the rock, the carbon that was in the CO2 in the air is transferred out of the atmosphere and eventually into the ocean, where it combines with calcium to form calcium carbonate and eventually settles to the seafloor as limestone, locked into the rock for millions of years. Carbon dioxide in, rock dissolved, carbon locked away. This is the silicate weathering thermostat. It was described in its mathematical form by James Walker and his colleagues James Hayes and James Kasting in 1981 in a paper that gave geologists and climate scientists their first rigorous framework for understanding how the planet had managed to stay habitable across billions of years despite the slow brightening of the sun and the dramatic variations in atmospheric composition. The thermostat works as a thermostat because the rate at which weathering removes CO2 increases when the planet is warmer. Warm air holds more water vapor, rainfall increases, the chemical reactions proceed faster, and decreases when the planet is colder. So if the planet gets too warm, CO2 is pulled down faster and the warming moderates. If the planet cools, weathering slows, CO2 builds up from volcanic sources and warmth returns. It is, in the ideal, a self-correcting system, a feedback loop that runs negative rather than positive, a mechanism for returning the planet to something like equilibrium across geological time. But it has a requirement. It needs liquid water. It needs rain. And on a frozen planet, there is almost no rain. This is the central trap within the trap. This is why Snowball Earth is not just an ordinary cold period that the weathering thermostat could have quietly corrected over a few million years. On a planet where the surface is entirely or almost entirely covered in ice and snow, the water cycle is not merely slowed, it is nearly shut off. The temperature at which ice sublimates, goes directly from solid to water vapor without passing through the liquid phase, is so cold, and the amount of water vapor a near -50-degree atmosphere can hold is so vanishingly small that precipitation becomes almost nothing. Not heavy rain dissolving rock and carrying CO2 to sea, not even light drizzle. Essentially nothing, a few traces of snow perhaps in some models, but the rivers have stopped. The liquid water that normally flows over rock and begins the chemical conversation that pulls CO2 out of the air. That water is gone, locked into the ice itself. The thermostat was switched off. Think of it as a car engine whose cooling system has seized. Normally, if the engine gets too hot, the coolant flows, the heat is carried away, the temperature comes back down. But if the coolant itself has frozen solid in the pipes, the normal cooling mechanism cannot function. Whatever happens inside the engine, the coolant cannot respond. The thermostat is there, the pipes are there, the radiator is there, but none of it matters because the working fluid is frozen. On Snowball Earth, the working fluid of the carbon cycle's thermostat, liquid water, was frozen across essentially the entire planetary surface. And so the thermostat sat inert, and the volcanoes kept breathing. Carbon dioxide went in, nothing came out. Month by month, year by year, century by century, the gas accumulated in the atmosphere with no mechanism to remove it. The air became, very slowly, more CO2-rich, not noticeably so in any single year, or any single decade, or any single millennium. The accumulation was glacially slow in every sense of the word, but it was relentless, and it was continuous, because the volcanoes, as we have established, never stopped. The geologist Paul Hoffman and the geochemist Daniel Schrag, who are among the most important figures in the modern development of the Snowball Earth hypothesis, who published a landmark paper in the journal Science in 1998 with colleagues, and who continued building the case in a major synthesis paper in Terra Nova in 2002, worked out the broad parameters of this process with the tools available from climate modeling and geochemistry. Their estimates, and the estimates of other researchers working on the problem from various angles, converged on a picture that is almost impossible to hold in the mind without a certain quiet awe. Over an estimated 4 to 30 million years, and that range reflects genuine uncertainty about the rates and the exact conditions, a humility that is worth noting. The atmospheric concentration of carbon dioxide on the frozen snowball Earth climbed to something in the order of 350 times its modern level. 350 times. To put that in terms of what modern atmospheric chemistry looks like, we measure atmospheric CO2 today in parts per million, and the current level is above 400 parts per million, which represents an increase of roughly 50% over the pre-industrial level and is already sufficient to drive measurable changes in the global climate. The CO2 concentration on a snowball Earth in its late stages was not 400 parts per million, it was not 1,000 parts per million, it was somewhere approaching 100,000 parts per million, roughly 0.1% of the entire atmosphere composed of carbon dioxide, or what scientists express as approximately 0.1 atmospheres. Hundreds of times today's concentration. The gas that we now watch with anxiety as it rises from its pre-industrial baseline, the gas that sits at the center of our contemporary conversations about the future of this planet's habitability, was 700 million years ago the only thing that could save the planet, the only rescue rope. And the process of acquiring enough of it to matter required at minimum millions of years of volcanic patience while the world sat frozen underneath a sky it could not change. This is the central irony of the snowball Earth escape, and it is worth sitting with in the way that the best ironies deserve. The gas that is now associated in much of our public conversation with danger and disruption, the warming agent whose rise we track and fear, was, in the most severe glacial crisis in Earth's history, the mechanism of salvation. Without it, the trap stayed shut. With enough of it, the trap broke open. The same chemical, the same mechanism, pointing in two completely different directions depending on the context, the concentration, and the planetary history surrounding it. Carbon dioxide, in other words, is not simply a villain or a savior. It is a variable, a dial. And on snowball Earth, that dial needed to be turned further than it had ever been turned before. But the story of how the CO2 accumulation ultimately broke the freeze, the story of the tipping point, the reverse runaway, the violent and astonishing thaw, that is the part that comes next. Before we reach it, there is something else worth knowing. Something that deepens the picture of what those millions of frozen years were actually like. Because the CO2 question is not the only puzzle the snowball Earth raises. There is another question, quieter, but in its own way, just as important. How did anything live? The hard snowball model, the Kirschvink and Hoffman version, with ice a kilometer thick at the equator and a surface temperature of -50 degrees Celsius, poses a problem for biology that is almost as severe as the one it poses for physics. Life on this planet, by the time of the Cryogenian, was not simple, not nothing. The first 1.5 billion years of Earth's history had produced microbial life of considerable sophistication, bacteria and archaea that had transformed the atmosphere, generated the oxygen, laid the groundwork for everything that would follow. And by the time of the Sturtian and Marinoan glaciations, the first eukaryotes, cells with nuclei, cells whose descendants would become every plant and animal and fungus that has ever lived, were already present. Early algae, the ancestors of creatures that need sunlight to survive. A kilometer of ice is, for sunlight, an almost total barrier. And yet the eukaryotes survived. They came through. The molecular evidence, the chemical signatures locked in the rocks, the earliest fossil traces, all of them indicate that the lineages which would eventually give rise to complex multicellular life were present before the Cryogenian glaciations and present after them. They endured. Something kept them alive through the long freeze. This survival is one of the pieces of evidence that feeds into a debate that runs alongside the Snowball Earth story and that has never been fully resolved. The debate between the hard snowball model and what is sometimes called the slushball model, or more precisely, between various versions of a fully frozen planet and versions in which some fraction of the surface remained, even barely, habitable. The slushball alternative, proposed by researchers including William Hyde and colleagues in a paper in the journal Nature in 2000, suggests that the global glaciation was severe but not total, that a thin belt of open or sea ice-covered water survived somewhere near the equator, not vast, not warm, not anything like a tropical ocean in any ordinary sense, but liquid, or near liquid, a narrow ring of relative refuge around the planet's middle where sunlight, even diminished and filtered through thin ice, could still reach photosynthesizing organisms, and where the temperatures, though extreme, were not the -50 of the polar ice sheets. Evidence cited in favor of some form of refugia is suggestive, even if not conclusive. Certain sedimentary structures in the glacial record appear to indicate open water conditions and active wave action during periods that should, on the hard snowball model, have been locked solid. And the survival of the eukaryotes themselves is evidence of a kind. If you need sunlight and liquid water, and you survived the cryogenian, you probably had access to sunlight and liquid water somewhere. The hard snowball researchers counter this with their own mechanisms for survival. Even under very thick equatorial ice, life might have found ways. Hydrothermal vents on the ocean floor, which are independent of sunlight and surface temperature, could have sustained chemotrophic communities. Life that draws energy from the chemical reactions of the venting rocks rather than from sunlight. Cracks in the ice, volcanic islands that punched through the cover, geothermally heated patches of ocean around submarine volcanoes. All of these could have provided refugia, however small and isolated. And some climate models suggest that even thick equatorial sea ice of the kind that might form if the ocean surface were colder than the deep interior heat was driving upward, could be relatively thin in places. Thin enough, perhaps, to transmit some fraction of sunlight. Thin enough for photosynthesis to happen, barely, in the gloom beneath. Hoffman and Schrag themselves pointed out that sea ice glaze of certain thickness would transmit enough diffuse light for a low rate of photosynthesis to proceed. Campbell and colleagues working on the problem later explored the conditions under which thin tropical sea ice might allow enough light through for the survival of photosynthetic organisms. The question of what the equatorial ice actually looked like, its thickness, its optical properties, its variability over millions of years, remains one of the genuinely open questions in the science of Snowball Earth, and the answer matters enormously for understanding how life endured and what it endured. The honest position, the one that the evidence warrants tonight, is that we do not know with certainty whether the snowball was hard or slushy. Scientists still argue, papers are still being written. The geological record, read by more and more sophisticated techniques in more and more laboratories around the world, keeps adding detail to a picture that remains, at its edges, blurry. Both models explain some things well and struggle with others. The debate is not a failure of science, but a sign of how genuinely difficult the questions are, and of how far back in time we are trying to look, and of how much can change in 650 million years of subsequent geological history that smears or erases or overwrites the evidence we would most like to have. What is not in debate is the large shape of the story. The ice reached the tropics, it stayed for a very long time. The planet was in a state from which ordinary processes could not easily recover it, and something did eventually break the trap. That something was the slow, patient, relentless accumulation of volcanic carbon dioxide in an atmosphere from which the rain-driven scrubber had been removed. The thermostat that Walker and Hayes and Kasting described, the thermostat that had kept the planet habitable through all the slow warming of the young sun and all the changes of atmosphere and ocean chemistry across billions of years. That thermostat was not destroyed, it was frozen, its components still existed. The rain, when it could fall again, would still dissolve CO2, and the dissolved CO2 would still react with rock, and the carbon would still find its way to the ocean floor. The mechanism was intact, it was simply not operating because its working fluid was locked in ice. And the volcanoes kept breathing, carbon dioxide went in, nothing came out. The sky grew richer, molecule by molecule, in the one gas that could eventually overpower the ice albedo feedback that had frozen the world in the first place. The same force that had locked the trap was now slowly and unknowingly accumulating the pressure that would break it. Consider for a moment the patience involved in what happened next. There is no human analogy that quite captures it. 1,000,000 years is a span of time that the human mind cannot hold as a felt thing. We can write the number, we can say the word, but we cannot experience it the way we experience a long afternoon, or a difficult year, or even the arc of a lifetime. 1,000,000 years is approximately the distance between us and the first rough stone tools our ancestors made on the African savanna, and even that comparison flattens the thing rather than illuminating it. Now take that span and multiply it by somewhere between 4 and 30. That is how long the volcanic carbon dioxide accumulated in the frozen sky before it reached the level needed to break the ice. 4 to 30 million years. The uncertainty in that range is not a failing of the science. It is a faithful report of how genuinely difficult it is to constrain the rate of volcanic outgassing on a planet that has been continuously rearranged for 600 million years since the events in question. Some models suggest the lower end of that range, some require the longer. What they agree on is the general scale, not thousands of years, not hundreds of thousands, millions upon millions, during which the atmosphere filled, molecule by molecule, with the gas that would eventually reopen the world. The concentration that had to be reached was extraordinary by any measure we use today. Atmospheric carbon dioxide in the modern era, the era of industrial emissions and international climate agreements and careful measurements at observatories on remote Pacific islands, runs at roughly 400 parts per million. That number is already higher than it has been for several million years, and its consequences are visible and measurable and the subject of considerable anxiety. Now hold that number in mind. The models suggest that to overwhelm the ice albedo feedback of a hard snowball Earth and tip the frozen planet back toward melting, atmospheric CO2 had to climb to somewhere in the vicinity of 350 times that modern level. Not 350 parts per million, 350 times the already elevated modern baseline. Something on the order of 1/10 of an atmosphere, 1 in 10 of every molecule you would have breathed, had you been there to breathe, would have been carbon dioxide. For comparison, the air we live in is roughly 21% oxygen and 78% nitrogen, and a little less than 0.5% of everything else combined, including that 1/4 millimeter slice of atmospheric CO2 we are currently so concerned about. The snowball escape required concentrations roughly 250 times what a human being can survive before losing consciousness. The planet was not preparing a gentle thaw, it was charging itself toward a detonation. The irony embedded in this number is one of the stranger facts in all of Earth's long history. Carbon dioxide is the gas we now treat as a kind of slow-moving threat, the molecule at the center of climate change, the byproduct of industrial civilization that we are collectively, and with considerable difficulty, trying to reduce. And yet in the cryogenian period, volcanic carbon dioxide was not a danger. It was the only possible rescue. Without it, the freeze would have been permanent, or at least permanent on any time scale that biological life, which is what we are discussing when we ask who eventually inherited this world, could have survived and eventually evolved through. The same molecule, the same chemistry, the same greenhouse physics. And the difference between a poison and a salvation is the context in which it operates. On a planet with a functioning hydrological cycle and liquid oceans and active weathering, excess CO2 drives warming that has consequences we are living with. On a planet frozen solid from pole to pole, with its rain scrubber switched off and its ocean locked beneath a kilometer of ice, CO2 was the slow turning of the only key available. Paul Hoffman and Daniel Schrag, whose work in the late 1990s and early 2000s brought the snowball Earth hypothesis to its modern, detailed, carefully evidenced form, described this accumulation in terms that are worth sitting with. The volcanic outgassing rate during the Cryogenian was not dramatically different from what it is today. Volcanoes then breathed roughly as they breathe now, exhaling carbon dioxide through rifts and calderas and submarine vents at a pace set by the planet's interior heat. What was different was the absence of the sink. Today, that volcanic output is roughly balanced by the slow removal of carbon through silicate weathering. Rain, rock, rivers, sea. The balance is not perfect and not instantaneous, but over geological timescales it holds, and it is what keeps Earth's temperature within the range that liquid water requires. On a snowball Earth, the sink was almost completely gone. Rain had not stopped everywhere entirely. Some models allow for a small residual water cycle, thin traces of atmospheric moisture completing abbreviated circuits over the ice. But the great weathering machine, the one that ingests CO2 by dissolving it into precipitation and feeding it through chemical reactions with silicate rock, was running at perhaps a few percent of its normal rate, possibly less. The volcanic source kept exhaling at roughly its ordinary pace. The sink had fallen nearly to zero, and so the gas accumulated with a patience that exceeds any human reckoning, until it reached the level that the physics of the atmosphere required for a thaw to become possible. There is a complication in this story, and it is worth spending time with because it sharpens the picture rather than muddying it. The complication is this: even reaching 350 times modern CO2 levels might not have been enough, at least not by itself, and not according to some of the most careful climate models that have tried to reproduce the deglaciation. Raymond Pierre Humbert, in work published in 2004, confronted what is sometimes called the hard-to-melt problem. The models he and others ran suggested that a fully glaciated snowball Earth with kilometer-thick equatorial ice, an albedo somewhere around 60 or 70%, and a faint young sun providing about 6% less energy than the sun delivers today, was remarkably resistant to melting even when atmospheric CO2 was pushed to very high levels. The ice would warm and begin to soften at the surface, but the sheer reflectivity of all that white ice, combined with the reduced solar input, made the system stubbornly resistant to the transition. The numbers demanded by the physics were high enough that some researchers wondered whether the timescale implied by the escape, millions of years of volcanic outgassing, was truly sufficient to produce them. This is not a contradiction of the core mechanism. Volcanic CO2 remains the engine of the escape. There is no serious alternative to it in the scientific literature, and the evidence in the rocks, particularly in the cap carbonate formations we will come to shortly, strongly supports the idea that CO2 reached extraordinary levels by the time the thaw arrived. But the hard-to-melt problem opened a question. Were there additional factors that helped the transition along, factors that acted alongside the CO2 accumulation to finally tip the frozen world back toward liquid water? Several candidates have been proposed and are still actively discussed. One of the more interesting is methane. Methane is a greenhouse gas significantly more potent than carbon dioxide. Molecule for molecule, over a century-scale timescale, it traps heat at a rate roughly 80 times higher than CO2, though it is shorter lived in the atmosphere, and eventually oxidizes to CO2 itself. Daniel Schrag and colleagues in work from 2002 raised the possibility that methane pulses might have played a role in both setting the stage for the freezes and potentially in helping end them. The frozen conditions of a snowball Earth ocean, with organic material buried beneath anoxic, ice-covered water, could in principle have created conditions favorable to methane production and occasional release. Whether such pulses were large enough and sustained enough to matter is still debated, and the evidence is indirect, but the possibility sits in the literature as a genuine contributing factor rather than a settled negative. A second candidate is dust. The ice of a snowball Earth was not pristine white throughout its entire multi-million-year duration. Volcanoes erupting through or around the ice margins would have deposited ash and fine particulates on the surface. Wind would have moved dust eroded from exposed rock, and the glacial process itself, grinding over continental surfaces, produces vast quantities of fine glacial flour that wind carries and deposits. Dark material on white ice is not a trivial consideration in the physics. The albedo of ice drops sharply when dust is present on its surface. The difference between clean white sea ice and dirty, dust-streaked glacier ice is measurable and significant. Dorian Abbott and Raymond Pierre Humbert, in work published in 2010, examined the role of dust more carefully and found that late in the glaciation, as volcanic and glacial processes deposited increasing amounts of dark material on the ice surface, the resulting reduction in albedo could have meaningfully lowered the CO2 threshold required to initiate melting. It is not that dust replaced CO2 as the escape mechanism. It is that dust may have been one of the factors that brought the required CO2 level within range of what the volcanoes could actually deliver in the time implied by the geological evidence. These details, methane and dust, are not the headline of the story. The headline remains volcanic CO2 accumulating in a frozen sky from which the rain scrubber had been removed. But they illustrate something important about how science actually works on questions this old and this complex. The planet did not escape through a single, clean mechanism with no complications. It escaped through a convergence, a primary driver, carbon dioxide, operating over millions of years, and a collection of secondary factors that together brought the system to the edge of the transition. The rock record that survived gives us the broad shape clearly enough. The fine grain, the exact timing, the precise concentrations, the relative contributions of different greenhouse gases is still being worked out. And then there is the other great open question of snowball Earth research, the one that sits beside the mechanism of escape and in some ways precedes it, because it bears on whether the mechanism of escape was the only thing that needed to happen or whether something else was going on as well. This is the question of what was happening inside the ice, or whether, in fact, the ice went all the way down. The hard snowball Earth model, as developed by Kirschvink and elaborated by Hoffman and Schrag and many colleagues, holds that the ocean was covered with ice from pole to pole, not a thin skim. A genuine, solid, planet-wide ice shell, potentially up to a kilometre thick at the equator, where paradoxically the ice was thinner than at higher latitudes because the equatorial regions receive more solar energy and the base of the ice sheet is closer to the geothermal warmth of the ocean floor. This is the model most people have in mind when they encounter the snowball Earth hypothesis. It is also the model that raises an immediate and troubling biological question. Photosynthesis requires light. Photosynthetic organisms, as the algae and cyanobacteria and their various relatives that were the foundation of Earth's food web in the cryogenian, require sunlight to penetrate to wherever they are living. A kilometre of ice does not transmit useful sunlight. A hard, thick, global ice shell is, from the perspective of any organism that needs to photosynthesize to live, essentially a light-proof lid clamped over the entire ocean. And yet photosynthetic life survived. We know this because photosynthetic descendants were present and functioning at the end of the snowball episodes. The eukaryotic lineages are the complex-celled organisms that would eventually give rise to algae, fungi, plants, and animals, passed through the cryogenian and emerged on the other side. If the ocean was truly sealed under a kilometer of light-proof ice for tens of millions of years, how? The hard snowball camp has answers, and they are worth examining carefully because they are not hand-waving. They are genuine proposals grounded in the physics and chemistry of ice and oceans and volcanic systems. One answer involves volcanic islands and seamounts. Earth's interior was as tectonically active during the cryogenian as it is today, which means that submarine volcanoes and volcanic island chains were erupting on a roughly continuous basis. Where a volcano breaks the surface, even through several hundred meters of ice, there is open water in the immediate vicinity of the heat source. Those small, scattered patches of open water around volcanic islands and hydrothermal vents could have served as refugia, islands of liquid and light in a frozen world, where photosynthetic life clung on. The refugia would have been small, scattered, and precarious, but small and precarious is enough to carry a lineage through if the lineage can survive there for long enough, and tens of millions of years is a very long time, even for a very small population in a very marginal environment. Another answer involves the optical properties of ice itself. Ice is not perfectly opaque. Thin ice transmits light, and even thick ice transmits a small fraction of incident sunlight, not enough for normal productivity, but potentially enough for survival at reduced rates. Work by Ian Campbell and colleagues in 2011 raised the possibility that even under hard snowball conditions, the equatorial ice, which was thinner than polar ice, perhaps 100 meters or so, rather than a kilometer, might have transmitted enough sunlight at its base to support a community of slow-growing, light-limited, but living photosynthetic organisms. The ice itself would have been what the researchers called sea glaze, thinner than the deep polar sheets, potentially clear enough at the base for filtered, dim, blue-green light to reach the water below. Not sunlight as we would recognize it. Something more like the diffuse, cold luminescence that reaches the underside of thick Arctic sea ice today, which is dim enough that organisms living there are working at the absolute margins of what photosynthesis can sustain, but enough. The alternative model, slushball Earth, first formally developed by William Hyde and colleagues in a 2000 paper in Nature, does not require these refugia arguments because it does not require the ocean to be completely sealed. The slushball model holds that the equatorial regions maintained a belt of open or very thinly iced ocean throughout the glaciation, a narrow ribbon of liquid tropical sea perhaps a few degrees of latitude wide. This belt would have remained ice-free or nearly so because of the geometry of solar energy delivery. The tropics receive more intense sunlight than the poles, and in the slushball model, that energy input was sufficient to prevent complete ice closure, even as ice sheets advanced from the poles and covered the vast majority of the ocean. If the slushball model is correct, then the survival of photosynthetic life through the cryogenian is not a problem requiring special explanation. It survived in the open tropical ocean, as life tends to do when there is open ocean available, and the mechanism of escape is slightly altered. Instead of volcanic CO2 accumulating in a completely closed system, there is some residual weathering happening in the thin tropical belt, some slow removal of CO2 through whatever marginal land or shallow water chemistry was possible in that narrow zone. The escape still requires CO2 buildup, still involves the same broken thermostat logic, but the thermostat was not quite as completely broken. It was running at perhaps 10 or 15% of its normal rate rather than 1 or 2%, which would affect the timescale and the final CO2 concentration required. The evidence cited for the slushball model, or at least for ice-free or minimally iced refugia of some kind, includes certain sedimentary structures found in cryogenian rocks that are interpreted as recording open water conditions during the glaciation, including features that suggest wave action and current activity rather than the stillness expected under permanent thick ice. Alexis Olcott and colleagues, in work published in 2005 in Science, pointed to biological and sedimentary evidence that organic activity continued through the Sturtian glaciation in patterns that are more consistent with refugia than with a completely frozen world. The hard snowball camp has responses to each of these points. The debate is genuine. No one has yet found the single decisive piece of evidence that settles it, partly because the evidence from 650 million years ago is fragmentary and ambiguous by nature, and partly because the question is subtle enough that different lines of evidence can be read in ways consistent with both models by careful researchers working in good faith. What is interesting about this debate, if you are willing to let it be interesting rather than frustrating, is what it reveals about the actual texture of science on questions this old. The broad shape is not in dispute. The world froze. The world thawed. CO2 was the mechanism of the thaw. The thaw was rapid and violent by geological standards. These things are not seriously contested. What is contested is the precise thickness of the equatorial ice, the exact width of any tropical refugia, the exact CO2 level required for the transition, and the contributions of secondary factors. These are not small questions. They matter for understanding how life survived and whether the escape was possible within the timescale the volcanic outgassing rate implies. But they are questions at the edges of a framework that is itself well established. The argument is about the thickness of the ice over the tropics, not about whether the world froze. And while those debates continue in journals and at conferences and in the careful, slow, evidence-by-evidence work of people who spend careers reading cryogenian rocks, there is another thread in the story of the frozen world that bears examining because it records something that was happening in the dark, inside the sealed ocean. That would become legible in the rock record in a way that is surprising even by the standards of this story. The ocean, sealed beneath the ice, was slowly running out of oxygen. This is not immediately obvious, but it follows from the physics almost inevitably. Atmospheric oxygen enters the ocean at the surface through gas exchange, the same process by which carbon dioxide enters rainwater, but in reverse, with oxygen dissolving into seawater at the air-sea interface. On a normal Earth, this process keeps the surface ocean supplied with dissolved oxygen, which then circulates through the ocean by mixing and current systems. Photosynthesis in the surface ocean also produces oxygen as a byproduct, replenishing the supply continuously. On a snowball Earth, both of these oxygen sources were blocked or severely reduced. A thick ice cover eliminates gas exchange between the atmosphere and the ocean. The barrier is physical, and it is nearly complete. And if photosynthesis was reduced to marginal activity in refugia around volcanic vents or in the thin tropical belt, the photosynthetic oxygen source was likewise dramatically reduced. The deep ocean, cut off from both atmospheric oxygen input and photosynthetic oxygen production, would have gradually become anoxic, depleted of dissolved oxygen, over the timescales we are discussing. An anoxic deep ocean does things that an oxygenated ocean does not. One of the most significant is its treatment of iron. Iron dissolved in seawater is quickly oxidized and precipitated when oxygen is present. It rusts, essentially, and settles to the seafloor. In the normal, oxygenated modern ocean, dissolved iron concentrations are extremely low because iron is rapidly removed by this oxidation. But in an anoxic, deep ocean, iron coming from hydrothermal vents and from the weathering of seafloor rock has no oxygen to react with. It remains dissolved. It accumulates. The deep ocean of a snowball Earth would have been, over millions of years, slowly loading with dissolved iron, building up a reservoir of reduced iron that was going nowhere because there was no oxygen to precipitate it and no open surface to expose it to the atmosphere. This is where something remarkable happens in the rock record. Geologists examining cryogenian sequences from around the world, in Australia, in Canada, in Africa, in China, have found layers of banded iron formations within or associated with the glacial deposits. Banded iron formations are sedimentary rocks composed of alternating layers of iron-rich and iron-poor material, typically chert and iron oxide, that were extremely common in the Archean and early Proterozoic, the first half of Earth's history, and then largely disappeared about 1.8 billion years ago. Their disappearance is generally attributed to the Great Oxidation Event of roughly 4 billion years ago, when atmospheric oxygen first rose to significant levels and began oxidizing the ocean's dissolved iron budget. After about 1.8 billion years ago, with the deep ocean oxygenated, banded iron formations essentially stopped forming, and then, in the cryogenian, they reappear. C. Klein and N. J. Bukes, among others who have examined these deposits, recognized that the reappearance of banded iron formations in glacial-era sediments was not random. It was an intelligible signal. The mechanism is clear enough in outline. The frozen ice cover cuts the deep ocean off from atmospheric oxygen. Dissolved iron accumulates over millions of years in an anoxic deep. When the ice finally breaks and oxygen recontacts the deep ocean, the iron precipitates rapidly, leaving behind the banded layers of iron oxide that we find today, interbedded with or capping the glacial sediments. This makes the banded iron formations found in cryogenian sequences one of the more elegant pieces of evidence in the entire snowball Earth story. They are not just consistent with a frozen, anoxic ocean. They require one. A banded iron formation of this type and age cannot easily form without a long period of ice-covered anoxia, followed by a relatively rapid reoxygenation event. Their presence in the rock record is an independent line of evidence, separate from the paleomagnetic data and the cap carbonates, that the ocean was sealed. They are, in a sense, the receipt from inside the prison, a record not of how the planet froze or thawed, but of what happened to the ocean chemistry in the long, dark interior of the glaciation. There is something quietly striking about this. The banded iron formations of the Archean, the rusty striped rocks that are mined today as iron ore in places like Western Australia and the Great Lakes region of North America, formed in an ancient world before oxygen was common, when iron could accumulate freely in a reducing ocean. They tell the story of an early Earth in which the chemistry of the air and sea was profoundly different from what we know now, and then they stopped forming, because oxygen changed the ocean and the conditions that allowed them no longer existed. The cryogenian banded iron formations are, in a sense, an echo, a brief, localized recreation of those Archean conditions, not because the atmosphere lost its oxygen globally, but because the ice lid sealed the deep ocean away from the oxygen that was present in the atmosphere above. The planet did not regress to its ancient state. The ice merely imposed a temporary partition between the oxygenated sky and the trapped anoxic deep. And in that dark interval, the chemistry of a much earlier Earth briefly returned, recorded itself in layers of iron and chert, and then ended when the ice broke and oxygen reached the deep again. The deep ocean, then, was not simply sitting still during the tens of millions of years of the Sturtian and Marinoan glaciations. It was chemically transforming. Iron was accumulating. Organic material, whatever fell from the marginal photosynthetic communities in the refugia or the thin tropical belt, was settling to an anoxic sea floor where it decomposed slowly, if at all, building up reservoirs of reduced carbon and nutrients that would eventually matter enormously when the world reopened. Above the ice, the sky was doing its own slow transformation. The CO2 continued to rise, the volcanoes breathed, the years passed, not in thousands, not in tens of thousands, but in millions. The faint young sun continued its gradual brightening, adding a small but real increment of additional solar energy to the frozen surface each million years. The dust from volcanic eruptions accumulated on the ice in places, darkening it, reducing its reflectivity in patches and streaks. The methane, produced in anoxic sediments beneath the ice in ways that are still being characterized, may have risen in pulses through cracks and fissures to add its more powerful greenhouse effect to the slowly warming sky. And the ice held. For a very long time, the ice held. The planet was not at the edge of its escape. It was deep within the trap, and the trap had a great deal of depth to it. The climate system of a fully glaciated snowball Earth is, as Pierre Humbert's careful modeling showed, remarkably resistant to perturbation. You could raise CO2 considerably and still not escape, because the albedo of the ice surface was simply returning so much of the sun's energy to space that the warming effect could not overcome the heat loss. The system was in a deeply stable state, not the stability of a healthy equilibrium, but the stability of a deep potential well, a bowl in the energy landscape of the climate system that required an extraordinary push to escape. The push was coming. It had been coming for millions of years, molecule by molecule, eruption by eruption, patient and entirely indifferent to the biological stakes riding on it. How much CO2 was actually in the sky at the moment the break arrived? That is the question the models argue about most intensely, and it is a question the rocks can only answer indirectly through the chemistry of the cap carbonates and the isotopic signatures preserved in limestone and dolostone of that age. The estimate of roughly 350 times modern levels is a model-derived figure, not a direct measurement. What the direct measurements can say is that the carbon isotope record of cryogenian carbonates shows enormous swings, signals of a carbon cycle that was operating under conditions very different from anything before or since, with biological productivity suppressed, volcanic and weathering carbon inputs running at unusual ratios, and the ocean chemistry fluctuating in ways that have left distinctive and readable marks in the D13C values of the rocks. The carbon isotope excursions associated with both the Sturtian and the Marinoan glaciations are among the largest in the geological record. They are not small blips in the data, they are dramatic departures that span millions of years and cross zero in ways that indicate fundamental disruptions to the global carbon cycle. They are consistent with a world in which biological productivity had been sharply reduced, in which the normal flux of organic carbon from the surface ocean to the seafloor had been interrupted, and in which volcanic and weathering inputs were dominating the carbon budget of the atmosphere and ocean in ways they normally do not. The carbon isotope record is not a thermometer. It does not directly tell you how much CO2 was in the sky, but it is a recorder of the state of the carbon cycle, and the state it records during the cryogenian glaciations is a state unlike anything seen in more ordinary geological times. And somewhere in that long, strange interval, with CO2 building in the sky, with iron accumulating in the anoxic deep, with life hanging on in refugia around volcanic vents, or in the thin tropical belt or under sea glaze ice, with dust darkening the surface in patches and methane rising in occasional pulses. Somewhere in that interval, the balance began to shift. Not all at once, not on a morning that any observer, had there been an observer, could have identified as the morning the world began to change. But in the slow, aggregate arithmetic of planetary climate, the warming forcing was creeping up on the cooling forcing. The greenhouse effect of the accumulated CO2 was growing. The albedo advantage of the ice was holding until it wasn't. Until some point, at some latitude, at some moment, the ice surface began to absorb more heat than it was releasing. And the ice, which had held for millions of years, began very slightly, barely perceptibly at first, to yield. What happened after that yielding began is where the story accelerates. But that acceleration is where this particular arc of the narrative must pause, because the break, and what it unleashed, and the extraordinary geological fingerprint it left in rocks on 6 continents, and the cascade of consequences for life itself. All of that belongs to the final movement of the descent. It is enough for now to hold the picture of what existed just before the break, a frozen world, a sky dense with carbon dioxide at levels the planet had not seen in hundreds of millions of years, an ocean sealed and dark and anoxic and rich with dissolved iron, life clinging on in the margins, and the slow thermodynamic pressure of millions of years of volcanic patience finally beginning to find its purchase on the ice. The trap was not yet broken, but it was, at last, beginning to give. And when it gave in the way that only planetary systems can. Not gradually, not with restraint, but with the full violence of a mechanism that has been under pressure for millions of years, suddenly discovering that the wall holding it back has cracked. The mathematics of it are almost elegant once you see them clearly. The same ice albedo feedback that had driven the planet into the freeze in the first place, that merciless self-reinforcing loop where ice reflects sunlight, which cools the surface, which makes more ice, which reflects more sunlight, was a wheel that could spin in both directions. What had once accelerated the freeze with such terrible efficiency now became the engine of the thaw. Once the greenhouse forcing of that accumulated carbon dioxide crossed the threshold and began melting ice at the margins, bare ocean was exposed. And bare ocean, dark and light-absorbing, is almost the opposite of ice. Where ice reflects away roughly 80 to 90% of the sunlight that falls on it, open ocean absorbs nearly all of it. And so the warming, once started, did not need to fight the ice so much as it needed to expose the ocean. And the ocean, once exposed, fought the ice for it. It ran backward. The whole machine ran backward. The equatorial ice, which had persisted for millions of years against every force the planet could bring to bear, began to melt from the margins inward. And as it melted, the albedo of the planet fell, rapidly, precipitously, because the proportion of the surface reflecting sunlight was shrinking and the proportion absorbing sunlight was growing. And the more sunlight the planet absorbed, the warmer it became, and the more ice it melted, and the lower the albedo fell and the more sunlight it absorbed. You can follow the logic. It is the same feedback, the same wheel, the same ruthless arithmetic. Only now it was spinning in the direction of warmth. Climate modelers who have tried to reconstruct this event have found that once the tipping point was crossed, the deglaciation, the complete melting of the global ice cover, may have happened in as little as a few thousand years. 2,000 years is a number that appears in some of the modeling work. 2,000 years to melt an ice sheet that had taken millions of years to build and that had covered the entire planet and that had been a kilometer thick at the equator. 2,000 years is nothing in the timescale we have been speaking in. It is barely a heartbeat in geological time. It is, by geological standards, instantaneous. Imagine the picture. A planet that has been encased in white for 50 million years, longer in the case of the Sturtian, suddenly beginning to change color. The white retreating toward the poles. The dark blue of open ocean spreading across what had been ice. The sunlight that had been bouncing back into space for geological ages now being swallowed by the sea. The temperatures climbing, the ice retreating faster, the ocean spreading farther, the temperatures climbing faster. It did not stop at zero. It did not stop at a mild, comfortable average. Because the carbon dioxide that had accumulated in the atmosphere over those millions of volcanic years was still there. It had not been removed. It could not be removed quickly because the silicate weathering thermostat is that slow process of rain dissolving CO2 into carbonic acid, and that acid weathering rock and locking the carbon into sediment and sea needed liquid water and exposed rock to operate, and even as the ice melted, the thermostat needed time to spin back up. The CO2 that had been the key to the escape was still hanging in the sky, and now it had no ice to fight. Now it had a dark, heat-absorbing ocean to work with. The planet overshot. Enormously, violently, almost incomprehensibly. The same world that had sat at roughly minus 50 degrees Celsius, 50 degrees below the freezing point of water, swung through zero, swung past the temperatures we call comfortable, swung past the temperatures we call warm, and kept climbing. The modeling work and the geochemical evidence suggest that global average temperatures may have reached somewhere in the neighborhood of 50 degrees Celsius in the aftermath of the melt. Some estimates for tropical regions push even higher. Where ice had been kilometers deep, the air above the ocean may have settled into a temperature more like the inside of a hot oven. The transition from a frozen prison world to a scorching hothouse may have happened, by geological standards, in an eye blink. Deep freeze to super greenhouse in what amounts to a geological instant. Paul Hoffman and Daniel Schrag, who more than anyone else built the modern framework for understanding this event, described the resulting world as a super greenhouse. That name is precise. It is not merely a warm world, it is a world where the greenhouse gas concentration is so extraordinary, and the albedo so low from the absence of ice, and the ocean so warm and dark, that the heat accumulates at a rate the planet has almost never experienced. The same gas that we now discuss with anxiety as a driver of warming, carbon dioxide, that molecule of one carbon and two oxygens whose rising concentration in our modern atmosphere is a subject of serious scientific and political concern. That gas had spent millions of years being the planet's only possible rescue, and now, with the rescue complete, it was driving an overshoot into conditions that were in their own way as extreme as the freeze had been. There is an irony in that which is worth sitting with quietly in the dark. The gas we fear is the same gas that saved the planet. The mechanism we now watch with worry is the same mechanism that, at a crucial and irreplaceable moment in Earth's history, was the only thermodynamic force capable of breaking a frozen world free from its own reflected sunlight. The story of Snowball Earth is, among other things, the story of carbon dioxide being, depending on the moment and the context and the quantities involved, both a trap and a key. And then the rocks remembered it all. This is the part that makes geologists catch their breath. Across the world, in South Australia, in Canada, in Namibia, in China, in Scandinavia, on 6 continents, there is a rock formation that should not exist, or rather, its existence is perfectly explicable, but only once you know the story, and then it becomes one of the most vivid and legible signatures that the geological record has ever produced. It is called a cap carbonate, and it is the physical fingerprint of the thaw. A cap carbonate is a layer of carbonate rock, limestone, dolostone, the kinds of rock that normally form in warm, shallow, chemically active seas. It sits directly on top of glacial deposits, directly, not separated by millennia of gradual transition, not preceded by layers of tidal flat sediment or beach sand or shallow marine accumulation. It sits there worldwide with what geologists describe as a knife-sharp contact, ice age rubble, the tillites and dropstones and glacially scoured rock, and then, with essentially no transition, warm water carbonate. The seam between them is a record of violent change. On one side of that seam, a frozen world. On the other, a chemistry of the ocean consistent with warm conditions and an explosion of carbonate precipitation. Paul Hoffman and colleagues documented this in their landmark 1998 paper in the journal Science, and the cap carbonates became one of the central pieces of evidence for the whole Snowball Earth framework. But they are not just a confirmation of an event. They are, in their physical details, a document of the event's character. And that character was not gentle. The cap carbonates carry within them structures that speak to conditions the modern ocean does not produce. Giant wave ripples, some of them enormous, larger than any that form in today's seas, are preserved in some cap carbonate layers, indicating ocean energy far beyond what the modern world generates. Sea floor crystal fans of aragonite, a form of calcium carbonate, precipitated directly from seawater that was so chemically extreme, so supersaturated with carbonate ions, that minerals were crystallizing on the ocean floor the way frost forms on a window pane. The structure, called a teepee, a buckled, tent-like deformation in the carbonate layer, appears in some formations, formed by the sheer pressure of rapid precipitation. Allen and Hoffman, writing in the journal Nature in 2005, documented the giant wave ripples in the cap carbonates of Namibia. Those ripples require waves of extraordinary size, driven by winds of extraordinary strength, over an ocean that was either very wide or very energetic, or both. They are an index of a world in upheaval, an ocean and atmosphere that had been locked in deep cold for millions of years and were now, suddenly, receiving an enormous pulse of solar energy that the ice had been returning to space, and that the dark ocean was now swallowing. And the cap carbonates carry a chemical signature as well. The ratio of carbon isotopes in the cap carbonates, what geologists write as D13C, the delta notation tracking the relative abundance of carbon-13 to carbon-12, shows a strong negative excursion. This means the carbonate being laid down was depleted in the heavier isotope. There are several ways to produce such a signal, and they reinforce each other in the snowball framework. During the freeze, biological productivity in the ocean had been dramatically reduced. Some models suggest it was nearly extinguished, certainly in the hard snowball scenario where the ocean was sealed under ice and cut off from sunlight. Biological productivity preferentially removes the lighter carbon-12 from seawater, so when productivity collapses, the signal shifts toward the heavy isotope during the freeze and then swings dramatically negative in the aftermath when that productivity is still suppressed, and massive volcanic and weathering carbon that hasn't been processed by biology, floods the system. The D13C excursion in the cap carbonates is consistent with a world where the biological carbon cycle had nearly shut down, and then volcanic and weathering processes restarted the geochemical carbon cycle with tremendous force before biology caught up. It is, taken together, a receipt. The cap carbonates are the geological world's receipt for an event that happened 635 million years ago and left no witness. They record the chemistry, the temperature, the energy, and the violence of the rebound in the language of mineralogy and isotope geochemistry. Geologists call them the fingerprint of a sudden, violent thaw. They are exactly that. And now back to the question that has been open since near the beginning of this descent, the question of life. The question of how any living thing and any organism at all survived tens of millions of years under conditions so extreme that they dwarf any ice age in the planet's later history. And the question of what happened to life after the thaw. We have spoken of the slushball model, the possibility, argued by researchers including Hyde and colleagues in their 2000 paper in the journal Nature, that the hard snowball scenario may be too extreme, that a narrow belt of open water or very thin ice may have persisted near the equator, even during the depths of the freeze. We have spoken of refugia, the volcanic islands, the hydrothermal systems, the hot springs, the cracks in the ice, where photosynthetic life might have clung to existence even under a hard snowball scenario. The work of Olcott and colleagues, published in the journal Science in 2005, found sedimentary evidence suggesting that complex eukaryotic life, the kind with organized cellular machinery, the ancestors of animals and plants, did survive through the cryogenian glaciations. Whatever the mechanism of survival, the fact of survival is not in serious dispute. life made it through. And what happened to life after the thaw is one of the most consequential and dramatic chapters in the history of biology on this planet. The violent thaw was not merely a climatic event, it was a geochemical event of extraordinary proportions, and geochemical events have biological consequences. When the ice melted and the super greenhouse took hold, the weathering of rock accelerated dramatically. The silicate weathering thermostat that had been nearly switched off for millions of years came roaring back online. Rock that had been locked under ice, chemically unreacted and unscrubbed by rain, was suddenly exposed to an atmosphere dense with carbon dioxide and to precipitation falling from a sky that was now, at last, wet again. That precipitation, laden with carbonic acid from all that atmospheric CO2, fell on freshly exposed continental rock and weathered it ferociously. And weathering, the chemical breakdown of rock, releases mineral nutrients. Among the most important of those nutrients is phosphorus. Phosphorus is, in a very real sense, the currency of biological productivity. It is an essential ingredient in DNA, in the energy molecule adenosine triphosphate, in cell membranes. In the modern ocean, phosphorus is often the limiting nutrient, the one in shortest supply relative to what organisms need. When phosphorus is scarce, life is constrained. When phosphorus floods in, life blooms. And after the Marinoan deglaciation roughly 635 million years ago, phosphorus flooded in. The work of Planavsky and colleagues, published in the journal Nature in 2010, documented the phosphorus nutrient pulse that followed the snowball events. Rivers carrying the products of intense weathering delivered enormous quantities of phosphorus to the ocean. The ocean, which had been nutrient depleted and largely anoxic under its ice cover, suddenly received a fertilizing pulse of a scale the biosphere had not experienced in hundreds of millions of years, if ever. The biological response was, by the standards of the Precambrian, explosive. Life, which had been constrained and stressed and reduced to refugia through the long freeze, found itself in a suddenly warm, nutrient-rich, thoroughly disrupted ocean, and began to diversify and multiply in ways that left marks in the rock record. But the nutrient pulse was only part of it. There was also the matter of oxygen. The Neoproterozoic oxygenation event is the name given to a significant rise in atmospheric and oceanic oxygen concentrations that occurred in the aftermath of the Cryogenian Eas glaciations. The history of oxygen on Earth is a long story in its own right, but the relevant part here is this. Oxygen in the atmosphere and the deep ocean was substantially lower in the Cryogenian than it would become in the Ediacaran period that followed. Under the ice, the ocean had been anoxic. We have spoken of this, of the dissolved iron building up in the sealed, oxygen-poor water, of the banded iron formations that reappeared when the ice broke and the iron met oxygen again. But after the thaw, oxygen rose. The weathering processes that flooded the ocean with nutrients also changed its chemistry. The biological productivity that the nutrients stimulated produced oxygen. And crucially, there were geochemical changes to the way organic carbon was being buried versus recycled. The balance of the carbon cycle shifted in ways that allowed more oxygen to accumulate in the atmosphere over time. Ockenshields Joe, reviewing the evidence in 2012, laid out the case for the Neoproterozoic oxygenation event as a real and significant rise in oxygen that the snowball and thaw cycle played a direct role in driving. The implications for life are profound. Oxygen is the energy currency of complex multicellular animals. The metabolic demands of an animal, an organism with many differentiated cell types, organs, muscles, a nervous system, are orders of magnitude higher than the metabolic demands of a single-celled organism. You cannot run an animal on the oxygen levels of a pre-cryogenian world. You need more. And after the snowball, more is what the atmosphere and ocean delivered. And so we come to the Ediacaran period, which begins at the end of the Marinoan glaciation 635 million years ago and lasts until roughly 539 million years ago, and we come to the first unambiguous, large, complex, multicellular organisms in the fossil record, the Ediacaran biota. They are strange creatures, partly strange because they are genuinely unlike anything alive today. Flat, frond-like, quilted, some of them, bodies that resemble air mattresses more than any familiar animal, organisms that absorbed nutrients directly through their surfaces rather than eating in any conventional sense. And partly strange because we are still arguing about what they were, precisely. Whether they were the direct ancestors of later animals or an evolutionary experiment that mostly ended in the Ediacaran, a separate attempt at complex multicellular life that was subsequently replaced by the lineages that gave rise to the Cambrian fauna. Among them is Dickinsonia. Dickinsonia is a fossil that turns up in Ediacaran rock on multiple continents, in the Flinders Ranges of South Australia, in the White Sea region of Russia, in other sites. It is oval, ribbed, sometimes as small as a few millimeters, sometimes growing to more than a meter in length. For a long time, its nature was debated. Was it a fungus, a lichen, an alga, some kind of protist? Analysis of biomarkers, the chemical fossils of organic molecules preserved in ancient rock alongside the physical fossil, has strengthened the case that Dickinsonia was an animal. Not a complicated animal by later standards, but an animal, a multicellular organism with the kind of molecular architecture that distinguishes animals from fungi and plants and algae. Its presence in the Ediacaran, in the immediate aftermath of the cryogenian glaciations, is part of the evidence that the freeze and thaw cycle was intimately connected to the emergence of animal life on this planet. Guy Narbonne, writing in 2005 on the Ediacaran biota, and Mary Droser and James Gayling, reviewing the Ediacaran fossil record in 2015, both situated these organisms in the context of the post-snowball world, a world that had just come through the most extreme climate event in Earth's history, and was now, for the first time, genuinely habitable by complex multicellular life in a way it had not been before. And the molecular clock work. Studies that use the rate of genetic mutation to estimate when lineages diverged, places the origin of metazoans, animals in the broadest sense, in the window immediately following the cryogenian. Douglas Irwin and colleagues, in a 2011 paper in the journal Science, reviewed the evidence and placed the emergence of the major animal groups in this post-snowball window. The freeze was a bottleneck. That much seems clear. Whatever diversity existed before, the cryogenian glaciations was compressed, stressed, reduced to what could survive in refugia and margins. But a bottleneck, in evolutionary biology, is not only a destruction, it is also a filter. It is also sometimes a forcing function, a pressure that drives the survivors into new forms, new metabolic strategies, new relationships with their environment. The organisms that came through the Sturtian and the Marinoan were not the same as the organisms that went in. They had been shaped, selected, changed by tens of millions of years of extreme pressure, and they emerged into an ocean that was newly warm, newly oxygenated, newly rich in phosphorus, newly disrupted in all the ways that ecological disruption can be paradoxically an invitation. And from that invitation, the Ediacaran biota arose, and from the Ediacaran world, the Cambrian would follow, the period of rapid animal diversification that fills the fossil record with the first representatives of nearly all the major animal body plans. But the Cambrian is a later chapter, a subsequent story. It is enough for now to stand at the Ediacaran and recognize what the snowball and thaw cycle delivered. It delivered an oxygenated world. It delivered a nutrient-flooded ocean. It delivered the conditions under which complex animals could exist. It delivered, in a very real sense, the biological future of this planet. The freeze was the prison. The CO2 was the slow-turning key. and the thaw was the door flung open on a world that had never quite existed before. There is one more thing to say about the structure of what happened, but about the shape of the whole story from freeze to thaw to aftermath. And it is this. It happened twice. Both the Sturtian and the Marinoan glaciations followed this same essential arc. The freeze, the switched-off weathering thermostat, the accumulating volcanic CO2, the tipping point, the reverse runaway, the super greenhouse overshoot, and then the silicate weathering thermostat finally spinning back up, rain returning to a warm world, CO2 being drawn down by the weathering of rock, the climate cooling back towards something more temperate. And then, the Gaskias, at roughly 580 million years ago, was another glaciation, but the evidence suggests it was not global, not a snowball. It was a severe ice age by ordinary standards, but not the planet-encasing catastrophe that the Sturtian and Marinoan had been. It is a useful contrast, a reminder that the cryogenian glaciations were not simply extreme ice ages. They were qualitatively different, a different class of event, a different magnitude of freezing, a different level of extremity. The self-regulating loop that the Sturtian and Marinoan each followed, freeze, broken thermostat, volcanic accumulation, reverse runaway, super greenhouse, thermostat restart, cooling, is in some ways a portrait of a planet that is both fragile and resilient. Fragile enough that a feedback loop, once tripped, can encase it in ice for 57 million years. Resilient enough that no matter how thoroughly it freezes, the volcanic engine of its own interior keeps working, keeps breathing CO2, keeps charging the atmosphere with the one thing that can break the freeze. The planet carries within itself, always, the mechanism of its own rescue. It just takes time. Millions upon millions of years of volcanic patience with the rain scrubber frozen off and nothing to interfere with the slow accumulation. And here we arrive at the question you may have been carrying through this whole descent, the question that is perhaps the most quietly extraordinary implication of everything the science has uncovered. We have been speaking of events that happened 635 to 717 million years ago in a world unimaginably remote from any human experience. We have been speaking of ice and rock and chemistry and carbon, but at the end of the Marinoan deglaciation, in the flood of phosphorus and the rise of oxygen and the warm, churning, disrupted Ediacaran ocean, something began that would not stop. Life, which had been held in suspension, compressed into refugia, reduced to its most basic forms and its most stress-tolerant expressions, now found an open door. And it walked through, and the organisms that walked through that door, over hundreds of millions of years of subsequent evolution, branching and diversifying and adapting and eventually producing the Cambrian explosion and the Devonian fish and the Carboniferous forests and the Mesozoic and the mammals and at last hominids. Those organisms were, in a sense, children of the thaw. We are children of the thaw. The oxygen in the air you are breathing right now, the air that is perhaps making your breathing slower and easier as you settle towards sleep. That oxygen's history is entangled with the snowball events. The carbon in your body, the phosphorus in your DNA, the cells that compose your tissues, the biological lineage that eventually produced them, passed through a bottleneck of frozen extremity and emerged into a post-snowball ocean that made complex animal life possible for the first time. You did not evolve from the creatures that survived the cryogenian, but you could not exist without them, and they could not have survived into a world capable of producing you without the volcanic patience of millions of years of CO2 accumulation, and without the knife-sharp seam in the cap, carbonates where the ice age ended and the warm ocean began. The rocks remember it. 635 million years later, in the Flinders Ranges of South Australia, where the Elatina Formation records glacial sediments deposited within 10 degrees of the paleo-equator, and in Namibia, where the carbonic giant ripples speak to an ocean in violent churning transition, and in the stratigraphic sequences on 6 continents where glacial rubble meets warm water limestone at a contact so sharp it has no gradation. In all of those places, the physical record of the most extraordinary climate event in Earth's known history is still legible, still readable to those who know the language of ancient stone. And the strange beauty of the whole story is this: it is a story without a villain. The ice was not a mistake, the carbon dioxide was not a mistake, the volcanic eruptions were not a mistake. The silicate weathering thermostat that went silent under a frozen sky was not malfunctioning. It was operating exactly as it always does, dependent on liquid water. And there was no liquid water, and so it waited. Everything in the story was simply a physical and chemical system doing what physical and chemical systems do, following the logic of energy and entropy and the slow arithmetic of planetary climate, and arriving eventually at the only outcome available: the thaw. The planet was always going to escape. Given enough time, and time is the one resource that geological processes have in abundance, the volcanic CO2 was always going to accumulate to the threshold. The ice albedo feedback was always going to tip into reverse. The super greenhouse was always going to burn off the ice. The question was never whether, but when and how violent the correction would be when it came, and the answer to how violent turned out to be very, very violent indeed. So violent that it rewrote the chemistry of the ocean and the composition of the atmosphere, and left evidence in rock formations on 6 continents that geologists are still reading today, still arguing over, still refining their understanding of. The story is not finished in the sense that the scientific debate continues. The hard snowball versus slushball argument has not been resolved. The exact CO2 concentrations, somewhere in the range of 350 times modern levels, perhaps higher, perhaps somewhat lower depending on the models and the assumptions, remain estimates, not certainties. The precise duration of the thaw, the exact mechanisms by which specific groups of organisms survived, the role of methane and dust and clouds in the details of the deglaciation. These are questions that researchers are still working through. The science of Snowball Earth is not a completed project. It is a live investigation with new data coming in from paleomagnetic studies and geochemical analyses and improved climate models, and with the central framework, the framework that Kirschvink named in 1992 and Hoffman and Schrag developed into a comprehensive theory in their 1998 science paper and their 2002 review, being tested and refined and argued over by researchers who take the evidence seriously and disagree productively about what it means. That is how science works, and the fact that the question is still open, still being argued, still yielding new layers of understanding, that is not a weakness of the framework. It is a sign of its depth. The events of 635 to 717 million years ago were so extreme and left such a complex and multi-continental record, and have such profound implications for understanding climate feedbacks and the history of life, that they will be generating new science for as long as there are geologists and paleoclimatologists curious enough to look. But what is not in serious dispute is the shape of the story. Ice encased the planet. Volcanoes kept breathing. Rain stopped washing carbon from the sky. CO2 accumulated for millions of years. The greenhouse overwhelmed the ice. The planet thawed in a geological instant. It overshot into a hothouse. The ocean flooded with nutrients and oxygen. Life diversified. We exist. That is the arc. And it is, when you hold it whole, one of the most remarkable arcs in the 4.5 billion year history of this world. The passages are quiet now. The ice is long gone, melted away into the chemistry of ancient seas, locked into the limestone of cap carbonates, dissolved into the oxygen of the air and the phosphorus of living cells. The Flinders Ranges still stand in South Australia, and the rock is still there if you know where to look, that knife-sharp seam between the glacial rubble and the warm water limestone, the boundary line between a frozen prison and an open world. On a still night in the outback, under the southern hemisphere stars, you could press your hand to that rock and know that you were touching the fingerprint of the most dramatic climate reversal in Earth's history. You could feel, in the cold of the stone, the memory of a colder time. And then you could step back and look up and breathe the oxygen that the post-snowball world helped make possible, and recognize, in whatever quiet way seems right to you, that the distance between that frozen world and this breathing moment is not as vast as the 600 million year number suggests. Every cell in your body carries biochemistry that was shaped, in part, by what survived the cryogenian. The evolutionary lineage that produced you passed through the bottleneck of the freeze and emerged into the phosphorus-flooded, oxygenated world that followed. You are, in a very real and non-metaphorical sense, part of the biological inheritance of the Thaw. If you feel moved to share where in the world you are listening from tonight, the particular corner of this planet that you occupy, wherever the ice has long since melted and the air is breathable, and the cap carbonates are sleeping peacefully under the continents millions of years removed from the violence that made them, I would genuinely like to know. The comments are there, and I read them. The geography of who is listening, scattered across this thawed and living world, is itself a kind of wonder. There are more stories here of the same slow and careful kind, more descents into old, unresolved atmospheric mysteries of deep time, and the processes that have made this world what it is. They are waiting whenever you want them. You have done enough for one night. The ice has been melted for 635 million years. The ocean is warm. The oxygen is plentiful. Whatever remains of the day can be set down now, gently, the way the carbonate settles onto the ocean floor. Slowly, layer by layer, until it is still. Lectures over. Even the professor sleeps. Good night.